In this video, I'll be explaining to you what is an acid and a base, but this time using the Bronsted-Lowry definition. So, Bronsted-Lowry definition. Now, we've talked about the 5 steps definition and the Arrhenius definition, and they seem pretty simple. This one is a little bit more complicated, because instead of focusing on ions or senses, Bronsted-Lowry focused on protons. So protons are the main thing here. Now, he said that what we call now a Bronsted-Lowry acid, so I'm just going to call it a Bl acid, will be a proton donor, and that will in most cases be an H+. So the acid will give an H+ to the compound that it is reacting with. I'll explain this better with an actual example. So then the Bronsted-Lowry base would simply be the proton acceptor. So it would be the compound that accepts that this H+, this hydrogen ion. Now let's do this with an actual reaction to picture it better. So let's say we have something like HNO3, and it is aqueous. Let me write this better. Okay, that looks better. And we have water too. So it is liquid. And then what the products would be NO3 minus aqueous and hydronium. Now, if you think about Arrhenius, you would definitely just say, oh, this is an Arrhenius acid. But we're talking about Bronsted-Lowry in this case, so it is a bit different. Now, you have to think about this way. So he said that an acid is a proton donor, so it will give us a proton. In this case, the proton is an H+. So this is our proton. So when you look at this reaction, you have to find the compound that is giving that H. So between this and this, in the products, which one loses an H and which one wins an a hydrogen. So the HNO3 passes to be an NO3 minus. So it is losing that H, so it means that it is giving it to the water. So this is what we call a Bronsted-Lowry acid, or simply an acid if you want to. And the H2O is accepting that hydrogen ion. So we know that a Bronsted-Lowry base is a proton acceptor. So if it is accepting that H+, it means that this is going to be our Bronsted-Lowry base. Okay? And yeah, so you have to look at the products and see what gained a proton and what lost a proton. So this one, the NO3 minus lost a proton, so the HNO3 would be the acid that gave that proton to water to form the hydronium. But you have to, in a Bronsted-Lowry definition, you have to name the products too. And you will not call them a base and an acid as well, because it would just confuse you. You will call them a conjugate acid or conjugate base. So conjugate acid and a conjugate base. So what you basically have to do is look at the reaction, saying that the products are actually the reactants in this case. So let's Let's do this on another page. So we'll basically say that NO3 minus, it is aqueous, plus the hydronium ion formed, in this case it is not formed because it is the reactant, this will form HNO3 and water. And we said that this is our acid and this is our base in the previous. It is the same, but it's the same case. So you have to look at it the same way. So which of this is giving off a proton? And when you look at this, H3O plus is becoming H2O. So it is losing or giving that H. So we will call this our conjugate acid, or C acid, or Ca if you want to. You can just call it Ca2. And you can see that the NO3 suddenly becomes an HNO3. So it accepted a proton or an H plus. So we will call this our conjugate base, or Cb. So you actually have to write this reaction as something like this: HNO3 aqueous plus H2O. You write an arrow like this that form the NO3. It's the same reaction that occurred in the last page. So it's just this one that inversed, and you will say that this has double arrows. So this can be the reactants, and these are the products, and it can be the other way around. So it could be like that. So if something occurs twice, you just put double-headed arrows to say that is what usually happens to Bronsted-Lowry reactions. Now let's do another example, another reaction. So we have NH3, it is aqueous. We have water again, double-headed arrows. This is indicating you that this is a Bronsted-Lowry reaction already. And NH4 plus hydroxide. So do the same thing. The NH3 first had 3 hydrogens, and now it has 4 hydrogens. And the H2O first had 2 hydrogens, and now it has 1. So the H2O lost one proton, so it gave us, it donated 1 hydrogen. So this is our acid. And it means that the NH3 accepted 1 hydrogen, so this is our base. And we already wrote the double-headed arrow, so one of these has to be our conjugate acid and conjugate base. So just look at it from the other direction. The OH minus became an H2O, so it gained a hydrogen. And the NH4 became an NHC, so it lost a hydrogen. So if it lost it, it donated it, so it is an acid, a conjugate acid in this case. And if the OH minus accepted it, it is a conjugate base. So after a little bit of practice, this becomes really easy. You just have to understand, you just have to picture which gave up a hydrogen ion and which lost or which accepted a hydrogen ion. And if you do that, you'll be able to tell the difference pretty quickly. But there's one more thing. We saw in the previous page that the H2O was a base, right? And then we see in this page that it was an acid. So when something can act as an acid and a base, we call that species amphoteric. So amphoteric. It means that it can be or can act as acid or base, or and. Actually, no, just or. And examples of amphoteric species are, well, water, alcohols, amino acids. I'm just gonna write it as AA. And, well, some metal cations. Some metal cations. But you only really have to know about H2O for now. You have to know that water can be an acid or a base. So whenever you see H2O, don't be like, oh, I remember that this was an acid. No, you have to use the same procedure until if it could be a base or an acid. So be careful about that.